So I think we'll start. We are just running little late in the schedule, but you have time. I think this room will be available, so you can continue hands-on up to 7 or something, as long as you wish to. Okay, but I will start with the talk. So Surya is joining us online from MPIFR. So he's going to guide us through the motivation of doing polarization study. So this session is about polarization study, motivation of doing polarization study, and as well as the methodology. So
yeah, it's up to you. Yeah, Surya, you can start. Yeah.
Okay, I hope I'm audible. Please let me know if I'm not. I cannot see you all. 1 second. So in case if anything says, just feel free to interrupt me or message me on chat. Thank you. Before I begin, I want to thank the organizers for giving me the chance. And my situation was not so good, but hopefully, hope you all learned something from my experiences. So before we begin, I want to start with a small demonstration. I want you all to take your right hand or your left hand, whatever you want to take, and align it as shown here on the screen. And I want you to rotate your thumb about your index finger. When you do that, I want you to see that the angle that between your thumb and your index finger is changing as you rotate the thumb. And this is basically, it's not that the angle actually is changing, it's rather that how we see it is actually just, it just appears to change essentially. And the reason why this is interesting and why I wanted you all to do this exercise right now is that sometimes it so happens that we will not see our own hand, but we'll just see the angle. And by studying the angle, by studying the changes in the angle, we can infer rotation happening. And this angle is provided to us by the polarization of light. Essentially, the polarization of light can track this angle. And before we describe what polarization of light is, I want to take you through some physics course and describe what light is. Light, as we know it, are the source-free solutions of Maxwell's equations. Basically, long story short, we have light as an electromagnetic transverse wave. If the light is going along z-axis, we have electric field and magnetic field doing wavy action along the perpendicular axis. And this is basically how a differential equation, wave equation looks like. Without going for basic, and we ignore magnetic field in all of astronomy because magnetic field does not do any work, so we cannot detect magnetic field. So let's just focus on the electric field for now. And what you're seeing in the middle of the screen is the wave equation, the plane wave equation solution of the wave equation. It has the angular frequency, which is omega, going from the right to left. We have the k bar, which gives us the propagation direction, sorry. And you have the complex electric field vector E naught bar, which is a 3-dimensional complex vector. All the information about the wave itself is encoded in this 3-dimensional complex vector. And since it's a complex vector, we take a real part of it because we want the electric field amplitude at some point in time to be real. So we have Gauss law, which tells us that electric field vector is transverse, meaning that the del of the E is to be 0. So that means that if we take the E naught bar that we have here, it's a 3-dimensional complex vector. There are 3 complex spatial degrees of freedom in that, and one of them is exhausted because of the Gauss law, and we still have 2 complex spatial degrees of freedom, and these 2 complex degrees of freedom is called polarization. And if we measure these 2 complex numbers, we have measured polarization. And as 2 complex numbers have 4 parameters, to describe polarization completely, we need 4 parameters. I want you to keep this in the back of your mind because we will always be seeing 4 parameters together. This is something as a small demonstration that I built. It's just nothing but a bunch of linear polarizers. Sorry for using linear polarizers just yet, but to give you an idea that this something looks like this. And that there's a lot of polarization sources already around us. For example, one of them is the LCD screen, which is my screen right now, and probably also your laptop screens. And they, if you can see this here, if you look along the up-down axis, it is basically dark. And if you look around the left-right axis, it is as bright as the light which is not going through the filter. This essentially means that the brightness depends on orientation. Which way you're looking at determines what brightness you have, and this is something that lets you see it in once. But this is with our screens, and obviously we want to do what we can do with astronomy also. To give you an idea of what polarization is, that I will not go to a lot of math, but just show you that what the electric field does is that it draws ellipse, which is known as the polarization ellipse, and you can basically label any way you want. So for this one, I'm getting up as north, down as south, and east and west. And I want you to note that if you're looking along this the line, then of course you're going to have a lot of brightness. That is the maximum brightness line. And if you're looking along the perpendicular to it, you have very less brightness. To give an idea again, that the amplitude of the wave is the brightness or the intensity. So the larger the disturbance, the larger the brightness, and so forth. And again, to repeat, the brightness is different along different orientations or different directions, and that's why this is called polarization. That is polarization basically, and it's not a direction also, because it's not going east or west, it's going east and west. That is, it's not going up, or down, up, down. It's the same thing. So it's not direction, but orientation. It will be clear in the next slide. So if we don't see if we don't use the animation, if we just put a phase number to each the point of as it traces, then we'll have something like this, where the phase goes from 0 to 360 degrees, essentially one whole revolution. And this is the polarization ellipse. This is the shape that light draws every cycle. So I call this the shape of light. It's not rigorous, but it goes. And the major axis is the black dashed line, and the minor axis is the red dotted line. Basically, it's more bright when you're looking along this axis, and less bright when you're looking along this axis. And of course, we also have a sense of rotation. It can go clockwise or counterclockwise, and that depends on the light. And to go back to the orientation, it's not east or west, but east and west, meaning it's all not just going along this, it's also going this. So we have to not think about directions anymore, but we have to think about orientations. To skip a lot of math, the 4 parameters which I talked about earlier, where you have 2 complex numbers, those 4 parameters can be this. There are many more, but this is one such 4 parameterizations. The first one is the total light intensity. That is if you can measure the intensity of light, then the total intensity that you get. And then the next one is the polarized light intensity. It is so when we talk about a general light, it's not that all light is polarized. General light is basically unpolarized light and some polarized light. So they need not always be the same. And then the next two are the angles. Essentially, the orientation is known as position angle or orientation, which is 180 degree periodic. Essentially, this is not 0 to 360, but 0 to 180. Essentially, it's the orientation. And we track the orientation of the major axis, essentially, as the position angle, meaning the black dashed line. And the epsilon is the tangent of the axle, is called the axial ratio, or the tan of epsilon is the ratio of the major axis and the minor axis. And we assign the sign of epsilon to show us the handedness, essentially, if it's going clockwise or counterclockwise. If it's not clear at this point, we can go ahead and it'll be more clear later. To go back to the example, what we show with the hand, essentially, if you have something rotating, in this case, on the left, there's a green vector rotating along a white vector. If we have a linear polarized light coming from this green vector, if we track the linear polarization, we will essentially be seeing something that we see on the right, that the position angle is also changing as it rotates. And this is the basic idea that we'll be exploring further in this session, that we will be studying position angles so that we can see rotation even when there is no rotation, even when we cannot actually see rotation happening. So the first insight, of course, will be that position angle that we will see is able to track the dynamics of the source. And then there are also more things that we can do with polarization, but the primary focus at this point is basically to see if we can infer rotation without seeing rotation happening. The source which I want to introduce you to is called the repeating fast radio burst 2018-09-16B, 0916B. It is a repeating FRB source. which was localized to somewhere in this point, which has no persistent radio source or whatnot. It has a really interesting V-shaped structure here, but we do not know why. And so the coolest thing about this FRB is that it's one of the few FRBs which have a periodicity in the active window. So I want you to think of it as the following. Think of it as a rainy season. It does not rain every day during rainy season, but it's that season where, it's more likely to get some rain activity. The same thing with this FRB, but it's not full year, but rather it has a 16.34 days cycle, which means that within 16.434 days window, it's only active. It only emits bursts within a 5.1 day active window, which you can see in this plot that we have. We can assign a phase to the periodicity, and then you can see that all the bursts are always around the same phases. And then when you average it over the cycles, you see a nice little histogram showing that the activity is indeed constrained to specific phases. I want to highlight here again that there is no short-term periodicity, meaning that if you observe the source for like 2-3 hours, you do not recover any periodicity. So the idea here is that there's a periodicity in the active window, but not within the activity itself. So this is what we're going to do in the next half an hour. We will, or 45 minutes. So we'll try to measure Stokes parameters. It's okay if you do not understand what these parameters are. I want to give you an overview before we get into it. So first thing is we'll measure Stokes parameters of the burst. And for that, we will do polarization calibration of the burst. And after that, we'll have to Faraday derotate the burst. And then, and only then, can we measure position angles of the burst with GMRT. The idea here, again, is the same, that we measure these angles to see if there is anything rotation happening so that we can understand why there is an active window periodicity. We'll get to it when we get there, so hop along for the ride. So the first thing is, what are Stokes parameters? So there's this G.G. Stokes professor who did a bunch of math to show in what way we can parameterize the 4 parameters required to parameterize the polarization information about the light. I will not go through the math, but it's really interesting the way he developed the model. And if you remember the 4 parameters we described about the polarization ellipse, that we have total intensity, polarized intensity, and position angle, which is psi, and the epsilon, which is the tan of the ratios. We see that if we write our I, V, Q, U, which are the 4 Stokes parameters, which may just think of them as labels at this point. If you write it like this, we can see that these are the Stokes parameters, which we sort of use abundantly in polarization. And the derivation of this is derived by Stokes, and we just use it ansatz. And if you look at it, if you stare at it much longer, you will realize that these actually are forming a 3D spherical geometry system where you have the 2 psi as the azimuth angle and the 2 epsilon as the latitude, the signed latitude. You don't have to worry about how we derive it, but we'll see what it actually means visually soon. The power of Stokes parameters is that all of these quantities are intensity-like quantities. They are not angles. And that enables us to measure them easily. Furthermore, the superpower of Stokes parameters is that you can take averages. So imagine if you have a collection of lights with different position angles, and then you cannot just take the sum of the position angles because that is meaningless. But if you add this, take the sum of the Stokes parameters, then you have something meaningful, that the resultant light will be something that has the following Stokes parameters. And this has implications further when we try to average over frequency channels. And so instead of adding position angles, all we have to do is to add these U's and Q's and then take the arctan and so. So to visualize what Stokes parameters are, we have to remember that our light is always doing an ellipse, but just because it collapsed into a line or a circle doesn't mean that it's not being an ellipse. It is still an ellipse. And this is where how we actually introduce Stokes parameters. So we have Q's and U's, and you can see that they're actually lines. So positive Q is x-axis, you can label it so. Negative Q is y-axis. Positive U is plus 45 degrees. Negative U is minus 45 degrees. Positive V is when you're rotating counterclockwise. Negative V is when you're rotating counterclockwise. So we have two parameters for the linear polarization and one parameter for the circular polarization. And the sign of circular polarization tells us what is the handedness, how it rotates. So usually in optics and so you measure Stokes parameters. We use these linear and circular polarization filters, something like this, and then do a bit of algebra. But in radio astronomy, what we do is that we can directly measure the E0 bar. That is, we can directly measure the complex amplitudes. And so to describe what radio telescope would do is that it can point, so it can take care of the k bar dot r, the dot product here, and then it can tune its frequencies and channelizes, so it can take care of the frequencies also. So it can directly measure this. But to make and also another important thing about radio telescopes are that it's easy to measure second order statistics, meaning something which has product of itself, something which has two terms within inside. We'll not worry about why it has the case, but just accept it. And let's begin with the most simplest way that our radio telescope is looking at some source, and it is emitting the intensities in two A and B components. Remember that there are only two two complex numbers that are there. So we're just taking the magnitudes of those two complex numbers, and I'm labeling that A and B. And this is our telescope is doing this for every frequency channel and every time bin. And we remember that if you have two complex numbers, the total intensity of the complex numbers will depend on this individual intensities, but also on the phase difference. So that means that there will be a phase dependency, and we do not want this phase dependency. We want things to be as simple as the sum of the intensity of the sum is the sum of the individual intensities. To do that, we have to choose A and B judiciously. And that is also provided by Stokes, which I will not go into details on how they derived it. But the idea is that we decompose our light, any given light, which looks like this, into two components, A and B, such that both the components are called oppositely polarized, meaning that they have opposite sense of rotation, meaning the first component is going counterclockwise, the second component is going clockwise, and they also have perpendicular orientations, meaning that the major axis of one component is the minor axis of the second component. This way, when you have both of them simultaneously, you call that oppositely polarized. So given this light with these Stokes parameters, you can compute the ZA and ZB, essentially the two complex numbers. And when doing so, the best part is that you can add the magnitudes squares to get the total intensity. 0.96 plus 0.28 is not 1, but 0.96 square plus 0.28 square is 1. I checked it. So that's the power of it. But in radio astronomy, we go much further. We are able to get all the second order products, meaning we get the magnitudes, but we also compute the cross correlation for every frequency channel and time being. That is essentially this cross correlation product. So if you think about it, we have two autocorrelations, meaning ZA star, which is autocorrelation, and ZA star, ZB, which is a complex number, and it also has two parameters. So in total, we are recovering 4 parameters. So we should be able to describe the entire polarization just based on this second order statistics. And so the nomenclature is that they're called coherence parameters, and they are labeled as AA, BB, CR, and CI. And so this is basically the magnitude squared, the magnitude square, and the real and the imaginary part of cross correlation term. And this is so constructed that our receivers and so everything is so constructed that our coherence parameters and our Stokes parameters are sort of algebraically related. So by measuring these coherence parameters, which are independent of however you want to construct your machine, you can derive Stokes parameters automatically. So it's easier. So first is the linear basis, so which is basically means that you have x's and y's. So we again have the same given light, and we are now decomposing into two linear components. Notice here that there is no any ellipse here. Both of them are lines, but the combination of both of them is still giving us something which looks like an ellipse. And this is only possible because of the way we have chosen x and y's, or the bases, or the A and B's. And we have the magnitudes and the phase. We'll get to that when we need that. And also notice here that the handedness is still there, even though it's a single line, the handedness is still there. So now if we compute the coherence matrix, we have these two complex numbers. So naturally we can compute the coherence matrix ourselves. And the algebra, which I have conveniently skipped, will give us the coherence matrix and Stokes parameters equivalence to be like this. So that essentially means that if you take the autocorrelation term, which is this, that is equal to I plus Q. And if you take the autocorrelation of ZY, which is this one, which is I minus Q. And you can really clearly see that this essentially sets Q to be 0, what is the case here. And this is how it's actually done, that observator gives us coherence parameters. And we realize, what is the basis, how are the feeds of the receiver, and then we use that to derive our Stokes parameters. Now, if you go to circular basis, which is also another basis, we see that this is how the decomposition looks like. We have the circular basis, which has opposite sense of rotations. And since it's the circular components, they do not have any position angles or so, because you're going to define an orientation there. And again, we can do the same thing, that we do a bunch of math, and we sort of find a coherence matrix in Stokes parameter, in terms of Stokes parameters, which you get something like this. And once you compare that with this, you basically can derive Stokes parameters from using circular basis. There is a mismatch here that the numbers match for I, V, but they do not match for Q and U. And I was wondering if anyone can figure it out later, not now, obviously, but they can figure out out loud to hear what they think. Also, another note here that the default basis from now on will be circular basis, as the data that I'll be presenting and what you'll be working on later is also with GMRT band 4, which is also in circular basis. So it's going to be our default basis from now on. So we have now at a point where we have measured circular Stokes parameters. Now the next step is to do polarization calibration. But before that, why do we even need to calibrate? The way we actually do polarization, why I need to calibrate, is that measuring polarization parameters is like measuring two complex numbers. And not only that, we are measuring them simultaneously, but independently. So no matter how precise you construct your telescope, the gains seen by one component, the complex gain seen by one component, is not the same as the other component. So that means that in this matrix equation transformation, we have A and B see different complex gains as GA and E power J phi A or so. This basically alters the polarization information. So we need to compensate for this. This compensation is called calibration procedure. So the idea is that we don't want them to be different, essentially. They can be something, but we just don't want them to be different. So that essentially means that we only care about the differential complex gain. So it can be, A can be anything, but B has to be something that A matches to. So we only care about the differential term. So we can transform it. I'm going to skip this math, but we can transform this such that we get transform our Jones matrix, essentially this matrix which transforms our two complex numbers to something which only takes care about the differential term. So we have the one absolute gain, which is just one scalar number, which is a real number. We have E power gamma plus J phi, where the gamma is the differential gain, which accounts for the gain variations between A and B, the amplitude variations, and phi, which accounts for the differential phase between A and B. And I have raised a question here: why is there no global phase term? And I want you to confirm yourselves that even if you introduce a global phase term, something that affects A and B, you're not going to change your Stokes parameters. We are guaranteed that. So that's why we don't care about the global phase term. Another question is, how many total degrees of freedom does the Jones matrix have? As I want you to figure it out and let me know. The three parameters I've told you, gain, differential phase, are like these. And these are what we'll have to find, basically, to calibration. So this is what in the Jones matrix, which affects the complex numbers. But if you go to the Stokes parameters, we get something which is known as the Mueller matrix. So which essentially doing a lot of math will show you give you something like this, where you have the G term, the gain term, the gamma, which is the differential gain, and the phi, which is the differential phase term. And here we'll have, since we are now in Stokes terms, we'll have to somehow use which basis we are talking about. If we talk about linear basis, then we'll have to keep track of IQUV. It's going to be IQUV for us, but if it's a circular basis, it will be IVQU. What essentially this means is that the autocorrelation terms, what Stokes parameters or autocorrelation terms gives us, which is not necessary. Just focus that it's IVQU for now because we are in circular basis. So if you look at the parameters, we have the gain, and the gain is affecting all the Stokes parameters, which is true for circular and linear. The differential gain is only affecting I and V. I'm only going to talk about circular from now on, and it's only affecting the Stokes I and Stokes V. The differential phase is only affecting Q and U phase. So what this essentially means is that if we even if any one parameter is off, the things that affect most affected are only two of Stokes parameters or so. And this is why now we understood why we have to do polar calibration, and the procedure for calibration is like this. So we take our telescope, we look at a reference source whose IQUV we know at every frequency channel, which is the orange source. And then we take the data, and then we go to a test source whose IQUV we want to study. And the Stokes parameters is IVQU because we are in circular basis. So the way we do is that we have a Mueller matrix, which is a linear transformation. So imagine that you're observing at the reference source whose IQUV you know, which will be as true reference because this is a true that we know, and reference because it's a reference source. And what we observe from the telescope will be the m times the 2 because the Mueller matrix applied on it. So using this, we'll have to somehow get an estimate of the Mueller matrix. And this is tricky because Mueller matrix has 7 free parameters. And so how are we going to get 7 free parameters when you will basically have 3 known things because 4 known things. So this is an underdetermined system. So that's why we'll have to get more data, either get more data or somehow parameterize a Mueller matrix itself that we have done before. So the idea is that we get some estimate of Mueller matrix, we take the inverse of the Mueller matrix, we apply it to the data that we get when you're the test source that we want to study to recover the true Stokes values. And we do this for every frequency channel. This is how the calibration procedure is actually done. So, and a very important step in FRB analysis would be that we'll have to do something called on minus off. Essentially, radio telescope by virtue of themselves, will be emitting some noise that is coming from the telescope itself, which is called the system observed. And so we have to subtract that when you're looking at the source because our source will also have that background information. So we'll have to remove that essentially. So that step is called on minus off, which is very important. And so we don't always have the luxury of having an reference source. So what people have done is that they build an reference source within the receiver. So if you look at this receiver, you will have something like this. If you look at the electronics, you'll have something called the noise generator, which basically puts equal power with equal phase in both R and N, which is basically the both components, the left and the right. And in doing so, it generates a pure U signal because only pure U signal is some which has equal power and equal phase in both R and L. So here I'm saying it's a pure U signal. So it doesn't mean it has to be 100% pure U. Even if it's a fraction of it, it's also is fine because it is pure, and that's all that matters to us. And so if you assume that this noise 2 is this, and if you assume that our Mueller matrix is M is this, then we can basically get the observed to be this, and we can solve for G square, phi, the differential phase, differential gain, and everything. And this is how basically calibration is done when you run some codes. And the beauty here is that you basically are getting all the 3 parameters easily right off the bat. And so this is how calibration is actually done. That's why they use U, so that it allows you to break the degeneracy essentially. And I want to ask you here, does the sign of phi matter? And you can answer me later. So pretend that we have done a noise diode observation. We have taken on a noise diode, off noise diode, we have subtracted on and off. Now I'm showing you Stokes parameters as a function of frequency here. The frequency axis is from 550 megahertz to 750 megahertz, also known as the GMRT band 4. And I'm showing the Stokes parameters in I, the Stokes V in green, the Q and U in blue and red. And on top, I'm showing you the cross phase, essentially the phi component. And I can get phi component easily because I know Q and U, so I can solve for phi, and that's what is shown in the top. And this is how a basic noise diode, dirty noise diode data looks like, essentially, which has been uncalibrated. And the idea now is to you solve for G, gamma, and phi, and then you generate a solution, and then you apply that solution, basically the inverse of it. So, but instead of relying on algebraic properties all the time, algebraic solutions, we can do something further. We can use some physics. Essentially, if you have two components, we basically are measuring ZR and ZL, and if there is a phase delay between the two hands, basically R and L, it only will affect the cross correlation term. And this phase delay has a nice little, we can model the phase delay essentially. So if you have any geometric phase, which is k bar dot r bar minus omega t, then the phase delay will have some function which looks like this, which is which I encourage you to do it on your own. And this phase delay is also known as cross hand delay because it's the delay between the two hands, the R and the L. And if there is a phase delay, if there is actually a cable delay, basically, if there's a difference in the length propagated by both of the hands, then if that is constant, then the phase delay is a function of frequency, meaning that you have 2 pi by c. If this is constant of frequency, then this is a linear function of f. So you can use this to actually parameterize your phi further. And that is what actually we do. And that is what actually we do. And you can see that it's already a good estimate because we already see something linear against frequency. That means that this is easily modelable with a linear function. So the way we derive that involves a bunch of math, which I don't want to go so much into, but to give you a super overview is that you can think of Q and U as cos and sine of some angles. This is what we have seen and the way we have derived Stokes parameters also. So you can combine them together, so saying like the Q is the real part and the U is the imaginary part, to something that looks like a complex sinusoid. And if the idea being is that these phi's are basically the phase components. So if you basically take an integration over the frequency and take the magnitude of the integration, then you can basically use this as a parameterization. Long story short is that you have some parameterization of how to determine what is the if phi is a function of theta bar, then you can get an estimate of theta bar, get a reasonable estimate by maximizing some quantity, which it's not clear at this point, I understand, but we'll see in action soon. And I will not go this until now, but there is a very hand-wavy way of saying why this works. Essentially that you want to minimize the variance of some parameter, and that means that you're maximizing this function. We'll worry about it once we do the thingy, and I'll explain it again then. But for now, the calibration solution, we generate the calibration solution. We do that by using this make pacv command, which you will do in the hands-on session. We will save the calibration solution in the pacv format, which is a PSRK format, which you will familiarize yourself with when you're doing the hands-on session. We get the gain solution algebraically, which is from this equation. We get the differential gain solution from this, which is also algebraic. We use the d-phase linear model to basically get the parameters, and this is how the function looks like. The d is in delay in nanoseconds, and which we estimate using the maximization strategy, and find out is basically the bias term. So once you do all of that, you'll get a plot like this, which will show you. And here I want you to look at this top right panel that shows you magnitude as a function of delays. So here you see that there's a nice little peak at one particular delay. This is what I mean by saying maximizing. This magnitude is nothing but the L as defined before. And we are looking for a peak of that. And we're taking that peak and saying that, hey, this is our estimate of the cable delay. Essentially, you can think that if we introduce a cable delay of this much cable delay has been introduced in the system by the system, and we compensate for it so that we achieve, so that we can have accurate polarization data. And so the idea again is the same. We have off, on, off. So we do on minus off. And this is the data is given in the black points in the middle panel. The linear fit is this, the blue line. And what you're looking at here is the data minus the fit, which has structures. And I want to ask you, why does it have structures at this point? But not worry if you do not understand where this plot is coming from, because you will be making this plot yourself when you're doing the hands-on session. So yeah, that is how we actually do calibration. If you have generated this plot, that means that you have generated a calibration solution. All that is left is to apply for it, which is what will be done during the hands-on session also. That is with using a noise chart. But if you want to use a reference source that is in the sky, which is this orange one, there is also a lot of things between us and the source. That is the interstellar medium, that's the ionosphere, and of course our telescope around the Earth. So we have to compensate for a lot of things along the line of sight, and that compensation is actually done also by the code, and we'll get to it when we run the code. So at this point, what you have done is that we have measured Stokes parameters. We understood why we have to calibrate, and we're going to calibrate. We have calibrated it. Now we look at something about Faraday derotation and what is Faraday rotation. Now it comes to measurement part. So if you take a linearly polarized light, which is given like this, I can decompose that into a circular basis, essentially the first, which is like rotating like this, and the second component, which is rotating clockwise. And if you have a magnetic field which is coming out, so the light is coming out of the screen or your projector screen, the magnetic field is also coming out. And also you have these charged particles. So when you have all of these combined, what essentially happens is that because of the handedness of the magnetic field and the handedness of the circular basis, it adds a phase delay to the first component in one sense, and the second component on the equal magnitude, but in the opposite sense. For example, here the phases of this first and second component are 60 degrees and minus 150 degrees. So it is adding minus 30 to the first component and plus 30 to the second component. What this essentially does is that it rotates your position angle. So it rotates your orientation of the light, of the linear polarized light. And this is called Faraday rotation. So I did not go into a lot of math, but there's a lot of math that goes into it. I encourage you to check it out. And the idea is basically that it does birefringence. And basically that one component sees one phase delay and the other component sees a different other phase delay. And this was first discovered by, of course, Michael Faraday, and it's called Faraday rotation. And the parameter that governs all of this is called the rotation measure, which is measured as the change in the angle by the wavelength, the difference of the wavelength squares. To give you another idea of the same phenomena, if you have an electrically polarized, linearly polarized light coming here through this, which is going through this medium, which has magnetic field along the propagation axis, by traveling some distance t, it will have rotated its orientation axis. Basically, the angle of rotation is here is beta, sorry. And the equation wise, there's only one equation governing Faraday rotation, that is PA of lambda is equal to PA at infinite frequency plus RM lambda square. The question I want to raise here is, so why is it infinite frequency and not infinite wavelength? Which makes more sense? But this is the equation that we use. And the math looks something like this. The rotation measure, you can derive the rotation measure something like this, which depends on the number density, the number of electrons that you have along the line of sight, and the magnetic field along the line of sight. And we don't have to worry about it, because the sciences we're going to do is very easily understandable if you just remember that there's magnetic field and the number density. The position angle, this is the same equation in the previous slide. The PA at any frequency or at any wavelength lambda is the PA at infinite frequency or 0 lambda plus Rm lambda square. And again, if we use the Q and the U notation of that, we derive, then we can write L exponential of 2j PA infinity plus Rm lambda square. And you can take the real and imaginary parts out and you will get this L cos something, Q is cos something, and U is sine something. So these are the equations that are known in Faraday rotation, and not to worry, because this is to visualize it, this is how it looks like. So I'm showing you a burst that you will be playing with in the hands-on session. It is the signal to noise of 97 burst in the 59243. You're looking at the dynamic spectrum of the Stokes I, Stokes Q, and Stokes U. And the x-axis is time in milliseconds. The y-axis is 550 to 750 megahertz, which is not going to change. The frequency axis is not going to change so much. And what I want to show you here is that you have these red, blue variations in Q and U happening. And these waves are called Faraday rotation. This is how you can visualize Faraday rotation. The total intensity will not be showing you this, but just that the Q and U are changing is going to show you this. And another thing that you can notice is that they seem to be flat across time. So the waves are always consistent across time, which basically is another test to see that waves in Q and U do not change with time, and we can average across time. And once we do that, we get something like this. So the Q and the U have been averaged over frequency, and the position angle has been computed after we take in the average, because we cannot average position angles. And the data is shown in black dots. The fits are shown in red and blue. You can see here that the x-axis is still the frequency, and the position angle is not linear. It is not looking linear, as it has sometimes smaller widths towards the lower frequencies and larger widths towards higher frequencies, because it's lambda square. And you have the Q and the U. And another thing to notice here is that the amplitude is not constant. The amplitude at the higher frequency is larger compared to the amplitude at lower frequencies. I want you all to also think and answer why that is the case. And if we plot the same plot in lambda square as x-axis, we can see that now it's linear. The widths of each sawtooth is the same across the band, essentially. And the sine waves, the sine is much more visible now. And just to show you that it's lambda square and not frequency. So how do we measure this? We again use measure another tool that is there in the hands-on session. We have measure RMPA spec. We again follow a principle that we want to maximize a quantity, and the maximum, the point where it has the maximum is what we assume as the rotation measure. And obviously, we do some time averaging, frequency downsampling, and on-off subtraction that you will see, do it yourself when you're doing the hands-on session. And in addition, to actually get some estimate and some error in the estimate, we do bootstrapping. Bootstrapping is basically that you have the whole data, you sample that, you make a subset of the data, and then you measure your RM and PA from that data, and then you do the same exercise for multiple times, and then you take the average of all the estimates that you have done, so that you get a robust estimate for the mean estimate and the error in it, which will be clear when you're doing the hands-on session, I promise you. So if you run this script, you will basically measure rotation measure and position angle at infinite frequency. So what you're going to see again here in the top left panel is the magnitude. Essentially, we're looking for a peak at the RM, and this one has a peak at around this point. And so we're going to say this is the peak RM, essentially. But we're going to take since we're doing a bootstrapping, we'll have the rotation measure histograms and position angle histograms in the top left panels. In the middle panel, you again have the data as a function of lambda square, so it should be linear. And the black is the data points with error bars. The blue is the fit. And the bottom panel shows you the residuals. We again see that the residuals are not Gaussian-like. They have some structures here. And I want you to ask again, why do we have these structures, and what can we do about it? And again, this is PA lambda square, one equation, Faraday rotation, that is it. So if we have done Faraday rotation, if you measure rotation measure, we can correct for it because we know the mathematical equation. So once we correct for it, we get something like this. So if we compare with slide 51, sorry. If we compare with slide 51, where we see these waves in Q's and U, notice here that there are no waves anymore. All Q looks like one color, and all U looks like it's one color. And this basically means that we have done a good job at Faraday derotating it, essentially correcting for the Faraday effect. And if you look at it as a lambda square, you see that we no longer see anything varying with lambda linearly lambda square. It is a flat PA, and the Q's and U also have this have no wavy structure that we saw before. This also shows us that this is how we have been Faraday corrected. And now if I take the calibrated and RM corrected burst, and if I average over the frequency in Stokes, which I can do, and I plot it, I'm gonna show you the Stokes as a function of the bin number, essentially time bin. So I'm showing the Stokes total intensity in the bottom panel in black, the Stokes Q in blue, and the Stokes U in red. And on the top panel, I'm showing you the position angle as a function of time. So I want to ask you, does this position angle look flat to you or not? And there's this curve. Is this curve real or is it not real, or what is this curve doing? More importantly, this is how we have, at this point, I can say that we have measured polarization calibration. So to give you a recap of the journey, we started with Stokes parameters. We polarization calibrated it. We did Faraday derotation. And then we able to measure the position angles at this point. Now, the whole idea has been that we measure these angles to see if we can infer the rotation. Now we start doing the science. So if we have done one observation with the GMRT, we have collected some number of bursts. I have done the same procedure. I measured position angles, and I've gone one step further and measured position angle at infinite frequency. What you're seeing now is each individual burst colored in different, plotted in different colors. You can see that this kind of U shape that we have seen before is still there here. I want to ask you now, do you think this is flat or not? And to give you to further convince you, what I have done is that this band that you see is the standard deviation. And this total observation is for 4 hours long. So on the basis of this, I think it is not so flat, but it's a bit flat. And what we can say is that the PA variability is less than 7 degrees over 4 hour long observation. To actually further convince us that this is indeed flat, what we can do is that we can show we can fit one RM and one PA to all the bursts. So every single dot here is what you're seeing is one burst, like one frequency channel of the burst, and we're taking all the bursts together and we are trying to fit PA lambda square to it. And once we do that, we see that it is working. One RM and one PA are actually indeed fitting, which shows that it is not changing over the course of observation. And remember that we still are seeing these structures here when you look at the data minus fit. And these structures are still going to be there. And yeah, these are the same structures that we have been seeing during calibration when you have linear model and when we are actually fitting also. So, but long story short, we have shown you that the one RM and one PA fits to all the data. That means that it is not changing. And this not changing part is actually true for all the observations that we have done, where the separation between the bursts is more than 1 hour. So that means that the non-variability result is actually true for more than one observation. So, and then to study the position angles, what we'll do is that since we have a rotation as an active window periodicity, we will be studying position angle two different ways. We'll study position angles in the same cycle, different phase, meaning that we'll keep the cycle constant and vary the phase to see if there's any variations. The other strategy is that we keep the phase constant and vary the cycles, which is essentially going along the red axis. This is sort of same as looking for changes within this rainy season and changes from one rainy season to another. Sorry. The idea is that when you have two things, we have to keep one constant and vary the other to see what is the effect. So if I take all the observations, all the measurements, and put them as a function of phase, the phase is the same as this phase here. What I see is that the individual measurements are shown with faint points, and the averaged are showing with the black squares. I see this. This is not so informative, but what we'll do is that we'll keep the cycle constant. So we have two such instances, which is the one ellipse here, where both the measurements are taken from cycle 53, and these two individual points here, where both them have been taken from cycle 55. And what I want to say is that since they're from the same cycle, and since we are seeing a difference in the position angle, so we can say that the PA variability within the cycle is from a few degrees of hour. And this is still tentative at this point because of the structures we see in the position angles, which requires a bit of more work. And if you keep the phase constant, essentially means that we are drawing a line on PA phase and selecting all those which are within this line. For example, this cluster of points here and this cluster of points here. And if I label them G1 and G2, we can see that they actually seem like they're changing with activity cycle or MJD. These two cluster of points are at the same phase, so we do not expect any phase-to-phase variations. And if we compute that, if we compute the variability, we see that it's actually around 0.1 degrees per day. So to recap, what we have measured is that we measured position angle variability to be less than 7 degrees or 4-hour long observation. PA variability within a cycle is around degrees per hour, and PA variability across cycle at same phase is 0.1 degree per day, which is not a lot. And the idea is again the same. We have measured the angles. We cannot see the star. Based on the measured angles, can we say something that explains the active window periodicity? That is, in this example, we do not see the hand. We only see the angles. And can we see the hand moving? So the first model is the simplest model, which something is like a rotational period. That is, the burst, we only see bursts when this patch of emission region, the orange emission region, is towards us. And we do not see the burst when it's away from us. If you have something like this, then we can assume that the rotational period is around the active window periodicity of 16.34 days. And that means that the rotation must be very slow. And another thing to notice here is that it is tracing the same shape all the time. That means that you will always have the same position angles at same phases across different cycles. So this essentially means that since the rotational period is long, we can accept that PA variability is going to be much less on 4-hour observation. And since it's rotating very slowly, we can also expect some PA variability within a cycle. But what we cannot expect is that PA variability across cycles at the same phase, which is a very small quantity. So this is wrong. This is cross. So another model that we can test is that for something which is precession. If you are not familiar with precession as I was, and if you can understand precession by following this emission region, this orange spot, and you can see that how it's going around the rotation axis. So if you not understand, it was not also clear to me how precession was functioning, and it took a lot of time for me, but you can keep staring at it to understand what precession is. So in precession, the precession in this model, the precessional period is 16.34 days, the active window periodicity, and the rotation is of the order of seconds because that's how physics tells us. Otherwise, it will not be it will not match. And activity is only active when it's towards us. You can straight away see some problems in this model that if we have rotation of the order of seconds, why do we not see any variability in our angles? That's one thing. And even if that's okay the case, then how do we have a 5-day active window if the rotation is if we do not expect to see any PA variability? That basically means that in precession models, we cannot have non-variability of position angles on 4-hour observation timescales. And also we cannot expect variability within the cycle because it will be, you cannot have one or two, you can only have one of them, and you can't have both at the same time. And naturally, since across cycles, it cannot be showing any variability also. So these are the arguments, but since so what we have shown here is that the precession is not going to work, only rotation is going to work. And since these two are tentative, there's also some other arguments which are put in this paper. So I ask you to check this paper if you're interested. So to recap, we have measured angles. And we are actually now one step closer to understanding what is the source doing. We cannot see the source, so we can only measure the angles, and based on that, we're trying to see what the source is doing. So insights from polarization, the first insight that we have given you is that position angle tracks the dynamics of the source. This source, we know for sure that the source is definitely not precessing, but we don't know if it might or might not be rotating, the FRB source. The second insight will be the rotation measure variance along line of sight. If you take any repeating FRB, if you measure the position angles if you measure the rotation measures as a function of time, you notice that in almost all of the cases, they are varying. For example, these three repeating FRBs detected by chime, this one detected by fast, and this one detected by GBT. And look at the time y-axis, it's in 20,000 or so. And it also did a sign flip. And this one by this FRB that we've shown, which actually is going like a step. And this the first repeating FRB, which is also varying. The idea that is seeming to be common across all the repeating FRBs is that the RMs are varying. And I also want to highlight a couple of talks here. We have on October 14th during the Science Week, there will be talks by Apurva Bera, Manisha, Manaswamy, and Visweshwar, who will be probably talking more about rotation measure variations, and I want you to also check them out. So that is the rotation measures. I am running out of time, so I'm not going to spend more time over that. The third insight which I want you to take from position polarization is that the position angle is intrinsic to the source. The rotation measure is along the line of sight, so things that are between you and the source. But position angle, that is related to the source, and you can use this position angle to understand what the sources are doing. I want to highlight two examples. The one example is of a 18.18 minute long period of transient, which has an 18-minute period, not like 16 days or so. And I want you to look at this dynamic spectrum, which is IQUV. Look at the time axis. This is emission lasting for seconds, not like FRBs, which last for milliseconds. And you can see clearly there is Faraday rotation happening, and also that the Faraday position angles is flat, because this is exactly what we have seen with our FRB before. So this may be something similar to the source. And to compare them, we have to study position angles of FRBs and position angles of these kind of sources so that we can compare and see if they're matching. The other source which I want to show you is in X-rays, which is called Hercules X1, which is an X-ray neutron star binary system. And polarization studies done in X-rays also reveal something which is sort of like variability across cycle at same phase in case of the FRB. And this also means that if this is also studied further and FRB is also studied further, we can sort of connect all these sources together to get a better understanding of what these sources are. I'm almost reaching the hour, so I'm going to stop here. I'm going to quickly recap that we have used angles to study dynamics of the source. There are rotation measure variations that are common across repeating FRBs, and the position angle is intrinsic to the source and can be used to compare different kinds of sources. There are many more things that I have not covered, but in the interest of time, and I think I have given you enough information already that you can learn things on your own as we go ahead. But I want to thank you all for your attention, and thanks again for letting me speak.